This talk is going to be about probabilistic data structures. Quickly before I start, who's heard of them before? Some people. Who have used them before, like actually in stuff you've written? Less people. Who know how they all work? You do. You can come back up. So I'm James. Hello. You've probably seen me around with Luke and other James. I help organize Brighton Java. I work here at Brandwatch, so I've had to come a really long way to give this talk. Very tiresome. I put this together because I find probabilistic data structures really interesting. They're super cool. They help you do stuff in memory, tiny footprint, awesome, good stuff. And we've been using them in production more and more over time. So what's this talk about? We're going to do broadly 4 things. First thing, get some motivation as to why you should care, because that's a good place to start. Once I've hopefully convinced you that you should care, we're going to look at 3 probabilistic data structures. I think they're in order of complexity. We're going to start off with Bloom filters, which I think are fairly simple. Then we're going to do count, min, sketch, which is a bit more involved, but still pretty understandable. Then we're going to do hyperlog, which is interesting, and we'll get there at the end. So, motivation. Why should you care? Why should you care about my talk? Why should you care about probabilistic data structures? Well, broadly, they let you perform particular operations in memory at a scale that you didn't think was possible. They dramatically reduce the memory footprint of doing particular things, which is really cool. If you like algorithms, they're awesome. If you like looking like a wizard, then they're awesome. If you've got colleagues that haven't heard them before and you use them, they'll think you're magic. If you tell people about them, they think you're really clever. So I'm here telling you about them. Let's get some motivation first. Here's a slide with some different ways of storing stuff. On the left, we've got tape, then we've got hard drives, then we've got solid state drives, then we've got memory. There are some different properties that we can say about these things. One is that the speed of access goes up as we go to the right. Would you agree? Yeah, still awake, good. Memory is really fast, SSD is less fast, spinning disk hard drive is less fast than that, and tape's kind of there just as a joke, really. You wouldn't really be using that to write programs with. Also, the cost goes up to the right as well. Memory for 1 gigabyte is much more expensive than a gigabyte of SSD, is much more expensive than a gigabyte of hard drive, and I assume is also much more expensive than tape, but I might be wrong, so I don't use tape. Ease of use as a developer also kind of goes up and to the right, because if I want to put stuff in memory in my program, I probably like make an array and put some stuff in it, or a linked list and I put some stuff in it, and it's in memory. Really easy. As you kind of go down this stack, you either end up having to write files in or out, or maybe use a database or something. For example, if I wanted to store some stuff in memory, I might use a set, Java util set. Maybe if I wanted to store loads of stuff on SSD, I might want to use something like, I don't know, Elasticsearch or Solr or a relational database, because it's better than writing files in and out. As I start getting down to hard drives, then it's like, oh, okay, well, maybe we need to use something like Hadoop, HDFS. It starts getting more clunky and a bit more difficult to work with. So we want to do stuff in memory because it's easy as a developer. But the problem is, on our servers, and I've got rid of tape at this point because the joke's old, the amount of memory we have in terms of gigabytes or terabytes per server is probably less than the amount of gigabytes or terabytes we have of SSDs, which is probably less than the amount of hard drives we can have by various constraining factors. So that's a problem. How can we do more stuff here is the whole reason that you should be interested in probabilistic data structures. Is that motivation enough to learn some things? Good. Right, probabilistic data structures. They allow you to do things in memory at a scale that you didn't think you could do before, and often with a really tiny memory footprint, which is really neat. They also have cool names, which make you sound really clever, which is great, and they're awesome. But the one thing that you have to know if you're using them, really important, is that you as a developer have to accept a predictable level of inaccuracy. So things won't be completely accurate, and you have to know that up front. You have to make sure that your users know that. You have to make sure that anyone who is doing stuff with your code knows that. Is that okay? Does that make sense? Some nods. So we're looking at 3 different probabilistic data structures tonight. 3 of them do 3 different things. The first one I think is the simplest. They're called Bloom filters. Who knows what a Bloom filter is? A bunch of people. Good. They have nothing to do with flowers. Bloom filters are for working out whether something is in a set or not. That's what they're for. So for each of these structures that we look at tonight, we're going to look at how you would do it naively in Java in a way that will blow up your heap. Then we'll have a look at the algorithm. Then we'll have a look at a library that will allow you to use these structures in your own time. And then we'll look at the heap again. And we'll follow that pattern for all three. So hopefully you'll see how they save you loads of memory. We begin with Bloom filters. They were, I believe, invented by somebody called Bloom. Hence the name. There you go. First of all, membership of a set. If you were doing it naively in Java, what data structure would you use? It's not a trick question. A set, yes. Here is some code. Imagine, and you wouldn't use strings for this, but this is just an example. You were recording the visitors that were coming to your website by their IP. You create a new set, java.util set. It's a new hash set. You add 3 visitors to your set, different IPs. Then, the set allows you to call contains to see whether that element is in the set or not. The first one was put into the set. It returns true. The last one wasn't put into the set. It returns false. First year Java programming stuff, really simple. And that's great, and sets are really good. And this works for our 3 things that we're putting in there. But what happens if we start putting lots of stuff in this set? Well, it gets a bit bad. Insertion time gets bigger as we go on. So I wrote a program, generated random UUIDs, put them in a set, and measured with the Guava stopwatch how long it took. My laptop was probably doing other stuff at the time, so this isn't a big, super performant machine. But the more things you put in the set, the longer it takes to put stuff in there. Who'd have thunk it? But 1 million elements going into a set took about 7 seconds on my laptop to fill up. But anyway, what about the JVM heap? At the lower end, it was quite hard to measure because the JVM reserves strings for various different other things. But you can see that as we start putting loads and loads of things into a set, we've got 1 million things in at the bottom, 264 megabytes of the heap was taken up with just a set full of strings, which is quite a lot. And if you think maybe we wanted 10 million in there or 100 million, think of a really big website that receives many, 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 many visitors a day. Suddenly our Java programs are storing a whole lot of crap on the heap that's really big and quite bad. So is there a cleverer way of doing it? Yes, there is. It's called Bloom filters. But what is a Bloom filter? So yes, they were invented by someone called Burton Howard Bloom, which is a wonderful name, much better than my name. And there's a paper which is linked at the bottom, which was from 1970. They had computers in 1970? Whoa, amazing. But it was a long time ago, and he wrote this paper called Space-Time Trade-offs in Hash Coding with Allowable Errors. Good on him. And that's pretty much what it does. So we'll have a look by example how it works. What's a Bloom filter? We initialize a Bloom filter. It gives us an array of bits. So things that could be 0 or 1. They initialize all as 0, all unset bits. That's the first part of a Bloom filter. The second part of a Bloom filter is some number of hash functions. They all need to be different. In this example, we're just going to use 2. But there are some number of hash functions that sit in front of this array of bits. Now, if we want to insert an element in, we run it through the hash functions. So this element here, this string, goes through the first hash function, and it maps to one of these bits in the array. It sets it to 1. It goes through the second hash function. It maps to one of the bits in the array. It sets it to 1. Does that make sense? Nods, that's good. Let's test whether something that isn't there, that's not in there. We run it through the first hash function. In this case, it collides, and it was set to 1 previously. We run it through the second hash function. It maps to something set to 0. So we know that that was not added to the Bloom filter. If we test that something is in the Bloom filter that definitely is there, we run it through those 2 hash functions again, and it maps to 1 and maps to 1. And at this point, the Bloom filter can tell you maybe. And that's the probabilistic part of this, is that there's some degree of predictable error where that could be wrong. but we'll know 100% sure if it's not in there, but it may be in there. So that's how a Bloom filter works. Are you all kind of following me so far? Cool. But how do I know what the error is? I hear you cry. Not really. There are two things that determine the performance. One of them is how many bits do we have in this array? How wide does it get? And that determines how many things we can potentially put in there. And also affecting performance is how many hash functions we have. And we'll see how that affects the heap in a second. But first, how do you use this in your own code? Because that's the most important thing. You want to look really clever to your friends. I suggest the Bloom filter for Java in the Guava library, Google's Java utils, wonderful amalgamation of awesome things. I'm not using Gradle here, clearly, because I'm not cool. That's the Maven dependency. Get Guava, and I've rewritten that example with a Bloom filter. So instead of initializing a set, we create a new Bloom filter, which is storing strings. And there's a static initializer here called create, and we give it two things. One of them is called a funnel. What's a funnel? It's just a way that determines how the hashing works. Guava comes with a whole bunch of funnels for strings, integers, longs, doubles already for you that you can just use. If you're going to be putting objects in there, you can write your own funnel. It just says how you hash it. Not that exciting. And you also give the Bloom filter how many elements you're expecting to put in there. In this particular case, we're expecting to put 10,000 elements in there. Well, we're not actually, we're putting 3. But you can specify it when you create it, how big you think it's going to get. And then if we use the Bloom filter, we can add stuff in, which is really easy. And instead of the set contains method, we have may contain, because maybe it might be in there. And in this case, the first one returns true, because we added it. And then the second one returns false, because we didn't. And there you go, you've used a Bloom filter in Java. Aren't you clever? Wonderful. So if you are using it in Java, using the default stuff up there, you get a 3% false positive rate. So there's a 3% chance it might say that it's in there when it's not in there. And you have to think, is that acceptable? If it's not acceptable, then you can tune it. You can give it another parameter. To tacked on the end, we can actually specify our required error rate. So instead of it being 0.03 here, we've gone to 0.005, which means that there's less chance of a false positive. But tweaking this parameter has an effect on the size of the Bloom filter. How and why? Firstly, insertion time. It was broadly much of a muchness with the time it took to stuff elements into a set. We were like 7 seconds to put everything into a set. It was like 5 for a Bloom filter. I might have been like downloading a file here or streaming a Spotify track or something. They're pretty much similar. So no issues with the insertion time. But the heap size is where it gets interesting. So if I'm using a Bloom filter to store 1 million elements, compared to my set in Java, which was 264 megabytes, my Bloom filter was actually 900K, which is like super small compared to the sets. Isn't that interesting? That's super cool. And you could think that if we're just 900K for 1 million elements, for 10 million, 100 million, 500 million, it's still like manageable in my tiny Java program, which is really nice. So if we start tweaking the size of the Bloom filter in that Guava parameter, saying, oh, I'm actually going to store, 1 million or maybe 10 or whatever, the width of that Bloom filter bit counter array, that's where it gets bigger. So as I say, I want to store more things, we have more bits. So if I'm going to store 10 things, it initializes with 40 bits. I just use the debugger to do this. If I want to store 1 million things, it gives me 3.6 million bits in my array, which is quite a lot, but it's still 900K on the heap. It's not 260 megabytes of Java set. So there you go. That's that. And if I want to tweak how accurate the Bloom filter is, by default, that 3% false positive rate gives us 5 different hash functions when the elements are going in and out. If I'm going to try and make it super accurate down here, it ends up doing 20 hashes for every insert and every read. So the more accurate we want it to be, the more hash functions that we have. And those are your 2 kind of dimensions. Bigger size, more bits, more accurate, more hashes. Does that make sense? Cool. That's about it for that. Why would you use them? One really good paper, which I forgot to put the link to, is this thing called One Hit Wonders. There's a site called Akamai, which get lots of traffic. What they wanted to do was a bit related to the cooldown that Matthew was talking about, was that if you visit the site once and once only, it doesn't want to do any expensive computation to serve you any data. It wants to just serve you a cache version. But if you keep coming back, then it wants to serve you more personalized content. And it does that by using a bloom filter, in that if you visit for one time, it checks if you're in the bloom filter. If you're not, it knows you definitely aren't, gives you a cache version. If you come back again, you're in the bloom filter, and most of the time, it will serve you up something more computationally expensive. Also, HBase and Cassandra use bloom filters to identify regions where things are stored, so that it can skip over very big searches as it's doing things. And we used it here for some real-time matching stuff. So we, this didn't make it into production, but we were trying to work out if a user searched for a huge amount of people on Twitter, say 10,000 users, 100,000 users, could we then feed that into the crawling pipeline to do specific matching and data processing for users? You don't want a user to store 100,000 authors into a database and every user to do that, because it suddenly gets really big. So you could just create a bloom filter. You could serialize the bloom filter and store it very compactly by compressing it. And then you could load it into your Storm topology or whatever you want on the fly. Cool. Bloom filter's done. Are we cool with bloom filters? Wicked. See, I'm down with the kids. Next thing that we're going to do, count, min, sketch. Not Dracula. Count, min, sketch is slightly newer than bloom filters. Why do you want to use count, min, sketch? So the first one that we did bloom filters for was for set membership. Is something in a set or not? This one is about keeping track of counts of things. How many times have I seen an element? It's for count tracking. I have seen the hashtag awesome 5 times. I've seen the hashtag even more awesome 10 times. That's why you use count, min, sketch. Because there's often lots and lots of things you want to track counts for, and it gets a bit big. Firstly, naive implementation. If you were going to do count tracking in Java naively, how would you do it? Someone said map. Yeah, you would use a map. In this example, I go one set of abstraction higher and use a multi-set in Guava, but that's actually just a map behind the scenes, which a multi-set of, have you used a multi-set before? No, all right, it's basically a hash map where the key is the thing that you're counting and the value is like an integer, just how many times you've seen it. So you create a new hash multi-set. I'm going to add some elements in it. This one, and I'm going to add that one twice. And then if I call .count on this one, it says 2, because it's put in there twice. And if I call it on this one, it says 0, because I didn't put it in there. Does that make sense? Cool. And it's just a map behind the scenes. Again, insertion time, same program, generate random UUIDs, stuff them into strings. It took about 4 seconds to put 1 million items in there. Heap size, more important, gets bigger. So 1 million items in a multi-set started to take up 234 megabytes of heap, which is quite a lot. And if you keep going up, that gets bigger, which is bad. So can we do this more cleverly? And the answer is, yeah, we can. We use count, min, sketch. What is it? 3 words there, count, because it counts stuff. Min, because it uses a minimum to work out the number, which I'll show you in a second. And sketch, because it was invented by Rolf Harris. It wasn't. It was called sketch because it's a rough idea of what the counts are. It's kind of a hand-wavy idea. And the paper, this isn't the original paper at the bottom. This is a more recent kind of original authors revisit their glory and show you how amazing they are. But it's about 5 pages long, and it's really easy to read, and it's really easy to understand. And it goes through the whole thing. But we'll give you a rough idea. So remember, the bloom filter was a simple one. This is like the intermediate one. Slightly more stuff. That's a count, min, sketch. This time, these aren't bits. They are counters. So they're like integers. And they have a width, which is how many counters do I have in each array? And it has a depth, which is how many rows of counters do I have? Are people still following me? We have rows of counters, some number of them. We'll go into how many you need in a sec. But the easiest way is just to show you an example. I'm going to cut this down to 3 so that stuff fits on the screen. We're going to count an element for the first time. This is the element that we said we've seen once. Each of these rows has a different hash function. They have to be different. That's really important. There's #1, #2, #3. They can be really simple hashes. First row of counters goes through the first hash function, maps to this counter here, increments it from 0 to 1. Second one, different hash function, maps to a different counter, increments it from 0 to 1. Third row, different hash function, maps to that counter, increments from 0 to 1. All good? Next one, add the same element again. Each hash function maps to the same area. 1 gets incremented to 2, 1 gets incremented to 2, 1 gets incremented to 2, because we've seen it twice. Good? Now, different element. Let's add a different element in. First row, first hash function maps to this counter, goes from 0 to 1, because it's the first time we've seen it. Second row, we have a hash collision, because this maps to the same counter. So instead of going from 0 to 1, it goes to 3. That looks a bit wrong. Whoops. Hash function 3 maps to this one, increments from 0 to 1. Follow? Right. Now we want to ask the count min sketch, how many times have we seen something? How many times have we seen the first element? It goes to here, first hash function, 2. Goes to there, second hash function, 3. Goes to there, third hash function, 2. And then it takes the minimum, hence the min. The minimum of 2, 3, and 2 is 2. It's seen it twice. Next element, how many times have we seen it? First row maps to 1. Second row maps to 3. Third row maps to 1. The minimum of 1, 3, 1 is 1. We've seen it once. That's how it works. That's count min sketch. How clever. How many rows of counters do you need? How wide does it have to be? Well, we'll get to that. The hashes themselves don't need to be complicated. They can be really simple. They don't have to be like cryptographic hashes. They can just be like simple things. In the original paper, they give like a little schematic for a simple hash. But they must all be different, because each row mapping to different things is the way that we get over the hash collisions. How do we tune the sketch? Well, it's slightly more complicated than the Bloom filter. The Bloom filter, you say, I want this many elements, and it gets bigger. This is slightly different. There are two things. It's a paper, it's an academic paper, so obviously they're Greek letters. There's epsilon and delta, obviously. Epsilon is the accepted error that I would expect for my counts to have. So how wrong can those counts be for me to be happy? Delta is the probability that the estimate is outside of the accepted error rate that I've said. Sounds weird the first time you read it. It took me a little while to understand. But if you have epsilon and you have delta, then you can calculate the width and the depth by plugging them into those equations. And those equations I'm not going to go into, but there is some maths you can do which will calculate how big the sketch has to be. And that's code from the library which you're going to use, which is this one. There's a ClearSpring Analytics stream library, which was written by the folks at Add This. They built an entire business out of adding little buttons next to blog posts that you can click and say that you share it or like it. I assume they had to count quite large numbers of things, so they open source all their probabilistic data structures, which is nice of them. In this, we'll rewrite our original example using count min sketch. We create a new count min sketch. There you go. 3 parameters. The first one is that epsilon. The second one is that delta. And then the third one, annoyingly, is a random seed. I assume for testing so that you can initialize the same thing again and again. But once you've initialized it, you can add some stuff in. You add the thing and the number of times that you want to add it. Add the first thing once, second thing once, third thing twice. Estimate the count of that third thing, it comes back with 2. Estimate the count of something we haven't seen before, 0. And that's it. You're now using count min sketch in your code. And again, people think you're really clever. Heap size, important stuff. Insertion time to begin with, pretty much the same as inserting into a multiset. It's not expensive to insert stuff, so I'm not going to hang around on this slide for very long. It's pretty much the same. Interesting stuff is, well, actually, you can't really compare, because with the Bloom filter, we scaled it with the number of things being put in, but count min sketch doesn't really work like that. It works with the accepted error that you're happy with. But remember that we did have a JVM heap of like 234 megabytes. Let's have a look at it in terms of epsilon and delta, the two things that you can tune it by. The width is the number of counters per row, and the depth is the number of rows of counters in the sketch. As epsilon, we're saying we're happy with less error on our counts, and the delta gets more accurate to say it's less likely to be outside of our error. Then we can see that we end up with like 17 rows of counters, sorry, 17 counters in a row, and 20,000 rows of counters. However, even here, where we could be potentially keeping track of, say, millions and millions of elements and how many times we've seen their counts, we're looking at 2.7 megabytes of heap compared to hundreds. And if you're happy with a rather fudgy error rate, so say maybe you didn't care about the numbers of the things you're tracking, but roughly what is the top 10 things that got bought today, or the top 10 visitors to my site, then you could be using absolutely tiny amounts of heap to do this, which is awesome. No database needed, no select star from table where count is greater than, this is just in memory. Awesome. Use cases, any kind of frequency tracking. How many times have I seen a thing? NLP, useful. Take a 90 gigabyte corpus of words, calculate the word counts, store them in count min sketch, 9 gigabytes. Fits in memory, great. There are two extensions which I will not go into because it would take too much time, but if you're interested, heavy hitters is really interesting. That uses a heap next to the count min sketch to keep the top X, so then you can do like Twitter trends stuff. Another extension, range queries in things like Solar, use this kind of technology. Look it up if you're interested. Count min sketch is now done. 2 out of 3 done. Was that okay? Cool. The complicated one, sorry. Hyperloglog, it has the stupidest name as well. What the hell is a hyperlog? Why is it hyper? Why are there 2 of them? I don't know. But we'll explain why. Why is it called that? Not going to jump straight into the algorithm. Lots of people download the paper, look at it, get their face absolutely melted by maths, and then just go, what the hell is this? I'm just going back to playing on the PlayStation, I don't care. So we'll try and give you some kind of like intuition as to why it's interesting. It's for cardinality though. So in my list of things, how many unique items are in there? That's the problem that it tries to solve. So what are my unique visitors to my site today, for example? Naively in Java, we could do it with a set again. Make a new set, store some strings. Notice that this one and this one are different. This one is adding the same thing 3 times. Mathematical properties of a set are that things are unique. So when we call .size, it says 3. We're all following. Cool. That's how a set works. Again, insertion time. Well, we've already done it. It went up as we inserted more things. Million elements, took 4 seconds to go in. I need to check the numbers on this next one because it was getting a bit different. But in my previous example where I put in 1 million elements, it was like 250 megabytes of heap. For some reason, I measured it wrong there. But we're talking hundreds of megabytes with 1 million elements in there. So, hyperloglog. But we have to gently walk into it because not only is it complicated, it's also an iteration on an iteration of various different techniques. Let's start off with something called linear counting. Who's heard of linear counting? No. There was a paper in 1990 called A Linear Time Probabilistic Counting Algorithm for Database Applications. Bedtime reading. The technique is kind of similar to Bloom filters. We start off with an array of bits. We use a hash function. We put something in it. We hash it just once, set a bit. Different element. We hash it, same hash function. It maps to a different bit. So this is like super like the Bloom filter right now. But now what we want to do is work out the cardinality of that. So how many unique elements have we found? There's a crap way of doing it. It just sort of works, but the variance is bad. We use an equation. So an estimate of the cardinality is minus the width of the counter bits, in this case 10, multiplied by the natural logarithm of the width minus the mask. The mask is the number of ones we have, divided by the width gives you the cardinality. So this would be minus 10 times the natural logarithm of 10 minus 2 divided by 10, and the answer to that is 2.2. We added 2 things in. So it's kind of almost correct, but not quite correct. But the bad thing about this is that as we talk about huge numbers of things, the variance gets awful and the accuracy gets terrible. But there's an intuition for you there. Does that intuition kind of make sense? We put stuff in bits, we do an algorithm. Cool. We move from linear counting into log-log. The paper was called Log-Log Counting of Large Cardinalities. And I don't know whether that was just like a cut and paste error and he only meant to do log once or something. I don't know. But anyway, log-log. This takes a similar approach to that, but does some clever things. Before we look at the clever things, I want to give you an intuition of how this works. Flipping coins. Has everyone flipped a coin before? Awesome. You all have fingers and money. If you flip a coin, you've got 50% chance of it being a head. You've got 50% chance of it being tails, unless you're a dodgy gambler person. But 50% chance, 50-50. Now, if I got 5 heads in a row, how many times have I flipped the coin? Don't know, like 30 times, 40 times to get that number in a row? Probably, maybe, don't know. What if I got 100 heads in a row? How many times do you reckon I flipped the coin? Probably a lot more in order to get that row of heads. So that intuition of how many things I see in a row roughly corresponds to how many things I've seen is where log-log comes in. Instead of flipping coins, let's flip hashes. So we add an element to log-log. We make a binary hash, and this is completely invented. I didn't actually hash it, but we make a binary hash representation, and then we count the number of leading zeros that we've seen on the hash. This starts with a 1, so we have 0 leading zeros. We have none. Second element, we hash it, binary hash. It has 1 0 at the start. So we've seen 1 0. Next element, binary hash, doesn't start with a 0, 0. What we can then do is find the maximum number of leading zeros, and we could feed it into an equally sort of crap estimation that 2 to the power of the leading zeros gives us a rough shot at the cardinality. In this case, it estimates 2, because we saw 1 leading 0 at maximum. 2 to the power of 1 is 2. Bad estimation. But do you follow the bad estimation? Sort of. Okay. This is where the authors get crazy with the math. And I'm not going to go into it super much, but take that idea. How can we make that more accurate? So they spend a lot of time talking about how do we make that more accurate. Well, one of the ways that you could make it more accurate is you could hash it loads of times, like maybe hash it 1,000 times and then take the average. Hash it 5,000 times, take the average. Because as you do more hashes, the probability of it being wrong goes down, according to the paper. But that gets really expensive because you don't want this 5,000 hash functions or whatever running every time you insert an element, because that would be really expensive. So what can we do? The thing you can do is called stochastic averaging, which I might have said stochastic or stochastic. I don't know what the correct one is. Stochastic averaging. There you go. Everyone's still awake. What they do, they define some number of buckets. A bucket is just an array of counters. So it makes it similar to count, min, sketch. You still hash stuff, except you take the prefix of the hash, that then maps to one of the buckets. And then the bit that's left, you count the number of zeros on the bit that's left. So the first one, we say that that maps to the first bucket, just as an example. It has no leading zeros. We then take the prefix of the first one, maps to a different bucket. Oh, it's got 2 leading zeros. Map it in there. Third one, that prefix, we say, oh, it maps to that bucket, and it's got 2 leading zeros after that, 2. And this technique allows you to not have to use thousands of different hash functions. It kind of, according to the crazy math, says that this is actually an acceptable way of doing it. And then the authors blind you with their amazing equation, which is, in order to compute the cardinality, we take 2 to the power of the sum of the maximum number of zeros divided by the buckets that we had, multiplied by the number of buckets, multiplied by everyone's favorite thing in Java, magic numbers. They define a range of magic numbers which map to how many things you've put in there. So if you put in 10 things, there'll be 1 magic number. If you put in 1,000,000 things, there'll be a different magic number. And they prove all this in the paper, and the maths is way beyond me. But with this equation, they can give you an estimate of the cardinality where the average error is 1.3 divided by the square root of the number of buckets. What does that mean? If there are 1,024 buckets, we have a 4% error margin on our cardinality estimate, which is pretty cool, especially because each of these buckets only needs to have 5 bits in each, which means that we can estimate with 4% accuracy the cardinality of millions of elements with only 5K of RAM. Mind-blowing. But they didn't stop there, because that's just log-log. What's hyperlog-log? Well, they came back again in 2007 with hyperlog-log, the analysis of a near-optimal cardinality estimation algorithm. Good for them. They just couldn't put it down, could they? They had to keep coming back. The observation in this paper is that they take all the stuff that they did with log-log, and they have their buckets, and they record the leading zeros in the buckets, except they find out that if you throw away the largest 30% of the buckets, just leave the remaining 70 with the smallest leading zero values, then the error goes down to 1.05 divided by the square root of the buckets, which if we have 1,024 buckets gives us a 3.2% margin of error. Then they go even further because they just couldn't stop there. And they found out that instead of doing a regular average on that power of 2, which is a geometric mean, if you do a harmonic mean instead, then you take it down to 3%. And that's where they stopped, because they probably either ran out of words on the LaTeX template or they got bored. But yeah, with 1,024 buckets, you can estimate the cardinality of really huge amounts of elements, millions, to 3% accuracy in a tiny amount of space in RAM. Anyway, algorithm over, how to use it in your code, because that's really complicated. Same library. It's also in that ClearSpring Analytics one. You've already imported that. Good for you. Hyperloglog is a new hyperloglog. 3% accuracy is a parameter. Add stuff in with .offer. Call cardinality, gives you 3. It's also in Redis as well. There's a PF value named after the author. I've forgotten how you pronounce his name, but the author of the hyperloglog paper. There's a Redis hyperloglog counter as well. And that's it. You've used hyperloglog in your code. Don't try and explain it to your colleagues. Just submit that in the pull request and be like, I understand this stuff. And they'll think you're really, really clever. What does it mean for numbers? Set insertion time of UUIDs up to 1 million. Insertion time to hyperloglog, pretty much the same. No performance problems there. Awesome bit coming up. JVM heap used. Cardinality. Look at that difference. So that's actually probably 250 because I typed it wrong. You're using absolutely bugger all heap to do cardinality estimates of massive amounts of data. And if you think you're maybe got a storm topology and you're keeping a running count of the cardinality of the things that you've seen, this, for your storm bolt, is much more favorable than something like that. Awesome. Why would you use it? Anywhere that you need to do cardinality, think of unique site visitors, think of estimates of big database tables, think of streams of data where you're going to be computing this stuff. And that's it. That's 3 probabilistic data structures, which I hope you understand a bit about now, and also have the code to go away and use it in your own Java projects where people think you're really clever. We looked at Bloom filters for testing set membership, count min sketch for counting stuff, and hyperloglog and some of the crazy math story behind it. And that's it. We can all go home now. Thank you very much.